Hello everyone, it's my honor to present our recent work with you. The outline of this presentation reads as follows. We will first look at DCOPs. Next, we will move to existing pruning techniques and tree-based complete search algorithms. Finally, we will focus on our proposed method. So, let's get started. DCOPs are a fundamental framework for coordinated and cooperative multi-agent systems. A DCOP can be defined by a tuple, including agents, variables, domains, and constraints. Each constraint defines the cost for the participants. Here, Fij is the constraint between xi and xj. The goal is to find an assignment to minimize the aggregated cost. A DCOP can be visualized by a constraint graph, in which the vertices denote the agents and the edges denote the constraints. A pseudo-tree is an ordered arrangement of a constraint graph and can be generated by a depth-first traverse. Tree-based complete search algorithms perform a systematic search on a pseudo-tree. Specifically, each agent AI traverses the subtree rooted at itself under the running context, and maintains several bounds to prune the search space. Existing pruning techniques. To the best of our knowledge, the existing pruning techniques for DCOPs are bound-dependent and require collecting more information to obtain test bounds. Our proposed BIP is a pruning technique independent of bounds. It can cut down the search space independently, utilizing only local constraints and running contexts. So, BIP dispenses with information collection. Before elaborating on BIP, I first introduce the following terms, definitions, and properties. The U is the solution space of U. The minus IU is the set of all value combinations of all the variables involved in U except xi. Di is a primary optimal threshold for d minus I on U if it's the best response of d minus I on U. As IU, defined as follows, is a subset of the solution space of U. It has two properties, based on which BIP is presented. Property 1. There existed at least one element in SU leading to the optimal cost in U. Property 2. Given two cost table, U and U prime, SAU equal to SAU prime, if they satisfy the following conditions. According to the property 2, we can obtain the desired subspace of a cost table from its partial information. Look into a DCOP. Given its pseudo-tree and a running context, U prime in the property 2 can be instantiated to the combination cost table of local constraints as an agent AI under context I. The cost table U in property 2 can be instantiated to the combination cost table of all constraints in the subproblem rooted at AI. We have proved that the instantiated cost tables satisfy the conditions presented in property 2. According to the definition of SIU, AI can compute at AUI utilizing only local constraints and running contexts. Theoretically, all the elements excluded from SUI can be pruned out. However, it's hard to do since pruning some elements requires agents at different branches to coordinate their assignment decisions. It's difficult to implement this in a distributed setting where agents at different branches assign their value independently. Therefore, we choose to prune some elements which only involves AI or the joint implementation by AI and one its child. Specifically, AI removes DVI from its domain, and AI suggests its child AC to remove DVI-CDI from its domain. Take the DCOP list as follows for example, where all the constraints are identical as shown on the right. U2 is shown here. All the elements in S2U2 are highlighted in bold. All the elements including x2 equal to 2 are not belonging to S2U2 and can be removed. Therefore, the dv2 equal to 2. In addition, all the elements including x2 equal to 1 and x3 equal to 0 or 2 are not belonging to S2U2 and can be removed. Therefore, dv2 1 equal to 0, 2. Each agent AI can compute removed values for itself and receive the ones from its parent. So, its domain pruned by BIP is given as following. The potential problem introduced by BIP is that it may expand the context on which the search results depends, so that there is not enough information for the existing checking mechanism to determine the validity of search results. And therefore, we further propose ATM, which can filter out unacceptable search results by checking the change of domains. ATM consists of two rows, as shown as follows. At last, we present our experiment results. Here are the evaluation criteria and the experimental configuration. That figure presents the experimental results under different numbers of agents under the board configuration. These BIP-based algorithms exhibit superiorities over their originals, and the advantage expands as k increases. And that figure presents the performance comparison under different numbers of agents under dense configuration. The following results show the performance comparison under different domain sizes under the bar configuration. And this figure presents the performance comparison under different numbers of agents under dense configuration. The following results show the performance comparison under different domain sizes under the bar configuration. That figure shows the performance comparison under different M1 on the gap-free network problem. To conclude, we propose a novel pruning technique, BIP, which utilizes only local constraint and running context to cut down the search space, and apply BIP to tree-based complete search algorithms. Then, demonstrate the superiority of BIP from experimental perspective. That's the end of my presentation. Thanks for listening.